Okay, so we'll see if it actually is live and if anyone's out there. So welcome folks at home, virtually or real. And here we have the 7th of October. Okay, so I'm missing Shilpa and Yobi. Huge. There's a couple of those coming back. Shaboom, shaboom. That's from the 6 solutions from last time. Okie dokie. All right, first off, to you, do you have some chapter 4 problems you've worked on and you'd like to ask about together with some of those ideas with bonding and with Vesper and polarity and sigma and pi and all that good stuff? If you mark some, this is your chance to ask. Okie dokie. Then it's back to gases. And for gases, then, we need to talk a little about the theory of gases. And also today about practically how we use them. Okay, here's a practical guide to gases. And we didn't get to it last time because, did we finish that problem? Here, let's see. No, we had one last problem we didn't finish. We got the liters of O2. Okay, so back up. When last we met, we burned some certain amount of octane. Was that right?
Yeah.
Was it a gram or how much was it, sir? Okay, so recall. 1 gram octane. And we got up to how many? Moles of O2, was that right? Did we get that far? Okay, what did we get for an answer?
0.11. I looked.
0.11 moles of O2.
Sorry, I'm late.
Okay, all right.
Oh, I can do that, sorry. I just don't know
So what we still need to do is we need to change it to the question asked about liters of O2. Please turn your phone off. And we're going to use what tool, can you guess, to get to liters of O2, Aaron? Pivnert, right. Everybody say Pivnert. Pivnert. So PV equals nRT. And the question originally asked for how many liters of O2 does this need? So that's why we're using Pivnert. So if liters of O2, then that's like what letter we need to sort of solve for, Lena? The V. So let's just move the P over there, put that puppy on the bottom. Life is good. Okay, we needed N. That's why we went to all that work to get the moles of O2, so 0.11. The R value, I'm going to let you look in your notes and find that R value. And in the meantime, I've got to see what temperature I told you. Did I tell you a temperature, Aaron?
297 Kelvin.
Thank you very much. Okay, can you fish around and find the right R value from last time? How about R for Rhea? So Rhea, take a look and see which one would fit in there based on the labels we've got. Moles, Kelvin, we'd like liters.
So is that 8.31?
That'd be the one of joules.
Oh,
Isn't it?
gosh. Yeah, you're right.
Yeah.
Um, Would it be the 0.0?
Yeah.
Okay. 0.0821.
Label?
ATM, is it
I want the whole label. It's got a big flipping
then
label.
L times,
Liters?
yeah, liters times ATM, so atmosphere pressure,
Over.
over mole times Kelvin.
Okay, here's why I want that, Rhea. You've got to like make sure then everything's in the right label. So we've got Kelvin, we got that from Aaron, we got the moles, and we need the P to be in what sort of label then to match up everybody in NOD, ATM. We need atmospheres for that sucker. I hope I gave you that. Did I give you that value or not? What did I give you?
0.974.
Okay. And now everything cancels, and I should end up with liters. So can you punch that out, grab a calculator? Boop, you'll need it later this hour anyway when we do our little prep project for the lab. Or next period if we don't get to it again. So let's just all get it, and then we can agree if we get the right thing. Okay. Tom, you got a calculator? Calculator?
Oh, let me see. It's buried up.
Yeah, we'll need it today, so best to get it out. Okay, how about no B? Let us know when you get that far.
I got 2 point, well, how many sequence? 2.75.
2.75. Does that check with others?
Yeah.
Label on it ends up being liters, right? Because everything else cancels. And only liters is left. And especially if you're either under pressure in atmospheres, or if you're new to kind of doing this, put in enough labels. You got to put in the labels for me anyway, but when you're doing the book work. But on the AP, put in enough so you know you're putting stuff in with the right label, okay? Because oftentimes they won't give you the perfect labels, and you'll have to like figure out, oh, which R do I need, blah, 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 blah. All right? Okay, now that was your worst case scenario, what we just did. Sarah,
Just real quick, we need to like memorize those 3 numbers that you gave us for R.
they give you 2 of them. The only one you really got to remember is the 65 or 62.4. That one I've memorized. The other 2 you'll get on the given information sheet on the AP. But that one is useful, and they normally don't give it to you, the stickers.
Is there a way, like online, is there a sheet of paper with all the things we'll get on the?
Absolutely. You just go to the AP College Board website, click on the Chem, and then you'll get to the given information at some point. Yeah.
Is the 62.4 value, is that not on it because they want you to remember it, or because you don't really?
I don't know. They're so random about what's on that sheet, and it has changed a little through the years what they give you. And I'll give you a copy of that in the spring while we're practicing for the test at that point too. But what can I say? I don't know why. I don't know what the purpose is to not give you that. I find it a very useful one because a lot of times you get torr, which is the same as millimeters of mercury. So the 62.4 value is a good one to know. Okay, why was this one such a pain? It's a pain because we had to do a separate gram to mole or whatever to mole problem, and then take that and put it in the Prib note. Often there's an easier way, and it's the discovered or figured out by Guy Lussac. So let's look at what he did in 1808. His observation was this. He said, hey, or attention, if temperature and pressure are constant, for instance, like they were in his lab, okay, probably in Paris, then a volume ratio equals a reacting mole ratio. And voila. What this really means for you and I is we can save time, okay? So let me cut to the chase. Why is this any good for us? What it means is if I've got a reaction, let's take a simple one, of 2H2 gas plus an O2 gas forms two waters as a gas. So if it's all gases, I can also read this, well, and you know this, right? I can read it the way we have today, 2 moles, 1 mole, 2 moles. But if it's the same temperature and pressure, Gay-Lussac said, oh, I can read this as 2 liters of H2 plus 1 liter of O2 forms 2 liters of H2O. And that will save you time. Because if they don't change anything, I can just use a ratio of liters instead of a ratio of moles, and I have to change moles to liters and blah, blah, blah. So it ends up being a couple steps quicker. You'll see that as we do some problems. No.
I think I might actually get it now, but the 22.4 liters of a gas is 1 mole. That's just kind of irrelevant here because we're just using ratios. We're not saying that 2 moles of H2 are 2 liters of H2, right? Okay, yeah.
Yeah, we're using a ratio here. That's all there is to it. So we're saying, okay, normally this equation is in moles, Noah, but I can read it in liters also if I keep the temperature and pressure the same. That's kind of what that's about. So, yeah, and that is the basis often of a multiple choice test question on the AP, using that idea, Lena.
So if they, in the problem, they don't give you a different temperature and pressure, you can just assume it's the same?
Yeah. And they will do that, the stinkers, okay? So they won't spell it out for you. You've got to read between the lines. You've got to say, okay, it's in a lab or whatever they might say, and then you realize that the temperature and pressure are not changing. Yeah, right, exactly. Okay, let's go to some other tidbits about gases you need to know. Sort of gassy tidbits. That doesn't sound good. Anyway. Gas mixtures. You know, what is this on the board? I can't even write on this. Gas, look at that. Who did that? Would they pour turpentine on here or something? Right there I can write. Okay, for gas mixtures, Pivner works here too. So if it's a mixture of 2 or more gases, don't worry, Pivnert also works. Here's why, because we have this thing with gases called a partial pressure. So the partial pressure is the pressure the gas would exert if it occupied the entire volume by itself. Go zoom in. It sounds a little weird. In other words, if I've got a balloon, the balloon could have a partial pressure, and I'll show you how to abbreviate that in a second, of O2 of 0.26 atmospheres. It could have a partial pressure of N2 at the same time of 0.61 atmospheres or whatever, maybe some third gas. But it doesn't really matter. The point is, these partials kind of like pretend, okay, let's pretend there's no N2 or other gases there. If it was all O2, it would be 0.26 worth of pressure. If it was all N2, it would be 0.61 of pressure, whatever it happens to be. And the total would just be whatever it adds up to. It doesn't have to be one, although sometimes it is 1 atmosphere, but whatever that is. And then, along with this idea, we've got Dalton's law of partial pressures, which says the total pressure from gases equals the sum of the partials. In other words, P total equals PA plus PB plus blah, 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 blah. Okay, which doesn't sound very interesting, but let's see where you're going to encounter this. Okay. Let's talk about wet gas problems. So a wet gas problem really is applicable because what often happens in science is a scientist will gather up the gas that's produced, and it's often produced when solutions made of water get together. So unfortunately, when you gather up and save an amount of gas, you often have some water vapor in there too. So you get some gas with water vapor also present. So of course, what you got to do is take the total and subtract out the pressure of the to get the pressure of the gas. So the total and Quinn? The water. So minus the P of the water to get the pressure of the gas. And then this is called you ready? It's now called a dry gas pressure. So it's like dry wine, okay? Dry gas pressure. So you've taken out the water. Let's do one so you see how this works. And although it might seem easy, again, it's every year on the AP in some form. So I think they find it rather important. Okay, if the vapor pressure, I'm going to abbreviate that if that's all right, of H2O is 23.76 millimeters of mercury at 25 degrees. Find the pressure of H2 collected at 25 degrees C above a water solution. Pressure in the room is 758 millimeters of mercury. So how about Tom? I simply got to do what subtraction here to get the pressure of my gas? Wait a minute. I said it and then I didn't write the right number, Tom. Sorry. I said 758 and like a dummy, I didn't put the 8. Now will be more possible, Tom.
Okay, so we use What does the VP stand for?
the vapor pressure. So I
Okay.
want the pressure of the other gas,
So,
which is hydrogen.
so you do what, or sorry, not 25, 200 and, or sorry,
No, you lost me. No, you don't need to do it with pressures here, Tom. Use this puppy.
Yeah, that's what I'm trying to do. Is PT the,
Yeah, where's the PT there? Which number?
I've seen the temperature, but now I'm not sure.
Temperature? No.
'Cause
Pressure.
T.
Yeah, which pressure is it?
No, T is total.
Oh.
T is
okay,
total, yeah,
okay,
so
okay.
total.
That makes sense, okay, sorry. I can't do mental math because I got very little.
You don't have to, you just gotta tell me which things to subtract, because I wanna write them down.
Okay, so you have a 23.76 plus, 50.
No, I'm not gonna begin with that.
Oh, okay.
I wanna solve for the pressure of the gas. So what do I gotta subtract?
Pressure of the gas, you do 758.
There you go, the total minus, Tom,
Total minus the vapor pressure,
which is,
22.76.
now you're cooking.
Okay, my brain's working again.
I know, I had to jumpstart you, but now you're doing okay. Okay, so somebody subtract that, or Tom, you can, and let's see how many millimeters of mercury that is. And I'll say P of H2. I forgot that's what I actually told you that it was. So the pressure of hydrogen,
But we've got 734.24.
734.24, thank you. Millimeters of H3. And now, make sure my folks at home can see that. No, they can't see any of that. All right, so there's that. And now the question, actually, that's what we're just working on. The question is, how many grams of H2 is this? But I gotta give you something else, I'll bet you. Okay, so this will be like a part B, all right? So there we got the pressure of the gas. I'm sorry I got really sloppy up there, but now let's say how many grams of that gas is there? Okay, I'll have to, or you got a question, Aaron?
Yeah, so for A, the temperature isn't really substantial unless it were different temperatures, right? Like for the 25 degrees Celsius.
That's right. So often you'll have in the AP problem something you don't need, but you might need it in part B or C. So don't despair if you have data that they give you that you haven't used or that you haven't used in part A. Okay, because now I bet you we're going to use it. Okay, so they want grams. I can't go there directly, but I could solve Pivnert for what? How should I do the rest of this? For Quinn? For moles. Let's get Pivnert for moles. PV equals nRT. Quinn solve it for N, and what do we get?
PV over RT.
Thank you. Okay, let's plug those puppies in there and get this. So I'm going to turn it around. Okay, the pressure, we went to all that work, and it's what number am I plugging in, Lena?
734.24.
Thank you. Good. And then the R value. Oh, back to Rhea. So now let's look at the different labels you got, and let's see if we can pick an R that's going to work here.
So this time, yeah,
Volume?
volume, yeah.
Oh, volume. Thank you. Okay, so then you got two things to do, Rhea.
Oh, great.
Yeah, lucky you.
Can I start with the R?
You may.
Thank you. So there, because we have millimeters of mercury, we use 62.4.
Don't
What do
even
you
mind
guys
it.
divide by that? We do divide by that.
Okay. Give me the label on that puppy, Rhea.
That is liters times milliliters of mercury divided by moles times Kelvin.
Okay, now back to your volume here.
Right, the
Rhea.
volume's in the question 152 milliliters
Right, and you need it,
in liters. So it'd be 0.152.
thank you, good going. So that's one reason that's nice to pick that R first, is then you realize the labels you need, don't you, for the rest of the problem. And then the temperature, gang, in Kelvin down here is 298. Is that what I gave you? I can't remember.
25 plus 273.
So 298. Good. Okay, can we have all punch that out? And you can do a little canceling. Hopefully you're going to get moles because you're solving for N anyway, moles of H2. Okay, no B, you there?
Yeah, I got 0.006.
Six, maybe another spot.
Yeah,
So-
it's 0 after that.
Thank you. Let's check with others.
Yeah.
Okay, now think of what you got, because you don't need your calculators now. You want the grams of it. So we're almost there. So we got 0.0060 moles H2. Typical AP question, including the multiple choice part. No B.
Well, since it's 1, you multiply by the number 1.
It would if it was H2.
Oh, okay. So you multiply by 2 grams over 1.
Beautiful. Okay, so it's 2.00 and that's per mole. So just double it and what do you get, Noah?
0.012.
Good. I don't know if there's another spotter there. I lost track of my sig figs. And then it's grams of H2. Yeah? So if you can do stuff mentally, do so. And there's a good one as Noah caught that you can do mentally.
Will we have a calculator throughout the entire AP test?
No, the multiple choice part, you get no calculator. So occasionally when I hit you over the head, it's because I wanted just to practice mental math, just like you were doing. So that's we'll get more and more into that as time goes on. So on the online questions and quizzes, it's your choice, but ideally you should use no calculator for the multiple choice ones as well.
What was the original question again?
I had two questions. The second one was how many grams of H2 is collected. So we had to get the moles and then change that to grams to do that.
And if we had 1g over mole, then it would be the wrong answer because it would be
Well,
grams
it's-
of H1.
Exactly. So if it was hydrogen atoms, then you'd use 1, but often, no, it's hydrogen gas, so we got to know it's 2 grams per mole. Glenn?
What reaction would you do to get hydrogen off water? Because if you put any of the alkali metals in water, you'll cause an explosion.
No, not all of them. Sodium will, but some of the others just react vigorously.
But
And
that's
they
causing an
produce-
explosion. I think lithium is the only one that doesn't cause an explosion. But it's-
Well, if you use small enough amounts, the explosion will be like this. So, it depends on what you use. Also, I can use group 2 ones too, and they don't explode at all.
that is
So
true.
if I have some magnesium, I can put that into hydrochloric acid solution. And just remember, all those solutions, gang, that we've always used, they're made with water. So they're still going to give you, if H2 gas comes off, they're still going to give you a wet gas. And you have to subtract out that darned value. They'll give you the value for water vapor for you to subtract out, but you have to be thinking about that. Okay? Good. Good discussion. We okay? That you don't need anymore. I don't believe. So we're going to skip it.
I guess the problem, I don't really get the partial pressure. Pressure with gas would exert.
Well, like, if you have a volume of oxygen in a container, and then you have a volume of nitrogen in a container, and you take both of those and stuff them into the same container, the pressure in the final container is the same as the pressure in the original two containers combined.
Okay.
And thank you, exactly.
That's the first thing I've said today that makes sense though.
And the reason that's nice to realize, well, let me back up. The reason for that is because what kind of distances are we talking in a gas between the particles? Small or big distances? Big distances. So what Quinn has said is really true, because if I stuff more gas in here, really they're so far apart, it's as if each gas is acting separately to make a little pressure against the sides of the containers. And the O ones are making their pressure, the same pressure as Quinn said they might have done over here on their own. The H ones are making this pressure, and then we just add the two pressures together. So that's the deal with the partial pressures. It's as if everybody was alone. Seems weird. We'll see when that assumption breaks down. Okay. Let's talk KMT. Not my favorite buzzword, but they started using it in the AP a couple years ago. Sometimes I just have to learn new languages from these AP people. So what's KMT? KMT is kinetic molecular theory. Now, I don't know if you can say KMT, probably not, but you'll know the parts of this theory because we'll go through it and use it in various realms, including quizzes. Okay, so here's some assumptions of that theory, okay? One is that gas particles move, and the collisions with the side of the container make what's called the pressure. And we just did this in my physics class. The collisions are elastic. So physicsy types, what does that mean if the collisions are elastic? What do they do or not do? Start us off, Tom.
When they collide and move apart, they will slowly drift back together.
Not only if they're attracted, but they're not necessarily always attracted.
They bounce back.
Yeah, they bounce back. Think of like billiard balls, okay? A pool, you're playing pool table, okay? So, no energy is lost or gained. That's the big deal. Because in physics, if it's not elastic, then often either something gets deformed or things stick together, and then it's a different type of collision altogether. We're going to assume that's not happening. No.
But isn't it possible that if there's too much pressure on a container, it can break?
Voila, good. So if it's really, really high pressure, you don't just have a problem that it'll break, you have a problem that the assumption that these guys don't attract or repel is bad. But that only happens, as we'll see, Noah, if the pressure's really high. If the pressure's like room pressure or whatever, this assumption works really well. But we're going to see exactly when and why that assumption breaks down. But you're on the right track already. Let's do 3. Okay, the volume of the particles themselves can be ignored. And this is what I talked to Aaron about earlier. It's because how far apart are these suckers? Right? Really, really far apart in relation to their size. Even the really big gas molecules, they're so far apart, it just doesn't really seem to matter. So the space they take up is not a big deal. Then, ordinarily, the attractions between the molecules can be ignored. Two more. The average kinetic energy, remember that's energy of movement, kinetic energy of the molecules is directly proportional to the temperature. And lastly, at a given temperature, all gases have the same average kinetic energy. I find 5 and 6 a little repetitive, but so be it. Here, let me make sure my folks at home got a chance to see that. See that? Yeah, I think so. The reality looks something like this. I can have big guys like uranium hexafluoride. It's a gas, believe it or not. Probably doesn't look like this, but I don't care. These guys are cruising around. And then I can have little guys for like H2. And the deal is, generally, the big guys with a big mass are moving how? On average? On average, it would be slow. And the little guys with a very low mass, on average, are moving
Fast.
Now, it's not always the same about every single uranium hexafluoride and every single H2, but on average, that's the deal. Bigger molecules so on average, bigger molecules tend to move slower. And tiny ones faster, so they have the same KE, kinetic energy. Why? Because kinetic energy, if you recall, it's 1/2 mass times velocity squared, okay? So that's important, the velocity and mass. They used to have you do calculations with that. They don't anymore. That equation's only just for your information. Okay? So big ones move slow, generally little ones. But occasionally you get a big fast one and you get a slow moving little one, whatever, you know. So just talking about averages here. But the same average kinetic energy is the same temperature. They're essentially the same thing. And that's what they'll test you on the AP. Every year there's some stinking multiple choice question which tries to trick you into saying like, we have a container of uranium hexafluoride and hydrogen atoms. You know, pick the one, explain the one with the greater kinetic energy. And then and then choices are like, well, hydrogen because they're so fast, or whatever because they're so. And then at the bottom they'll be like, well, it's the same because it's the same temperature, and you got to go with that. So they have the same average kinetic energy. So if you know this and understand it, you'll get that one right every year. No,
In this example, is the kinetic energy the speed at which they're like
it's both. It's
the
a
relative
combination of speed and mass,
okay.
both together. Okay, take a break. We'll do our little prep thing afterwards, and away we go. Okay, back to this guy.
Mr. Wellborn has been to my house. He brought us cookies. Mr. Mandel has been to my house. Because basically we're trying to get children. Mr. Wellborn's child is in 5th grade. My little brother's trying. It's so fun. Sorry, no. Okay, you would.
Mm.
My brother was the president of NHS, so we get to host like their club. And this was you always thought that.
It's not screwed in very tight.
I've already done it.
Standing in the background of the patient are like.
That's not gonna be the case though. You're not gonna be with the doctor the entire time.
Ja, nach dem Fall, aber das ist
Ja, immer noch. Zwei Wochen.
Okay, so we'll see where this thing breaks down, this theory breaks down another day. But that's as far as I want to get with you right now. And then we're going to go to the lab. Well, right here. And I'm going to show you the setup by getting all this junk out of our way. And I'm going to give you the lab right now. Our setup will vary a little bit because I've done this so many years. I know a better way to do it. Please. Yeah, and she'll be there because we're doing it on Monday, so that's good. You know, did I show you one? Okay, so the purpose is, Quinn, what of this lab?
Purpose of the experiment, determine the density of the vapor of an volatile liquid. Use the calculated density and the ideal gas calculation to calculate the molar mass of the liquid.
Okay, so the formula is on the next page, so flip to that. And they use MM for molar mass, so that's equation 6, basically. And RT and P, you know, and D is going to stand for, in this lab, the density. And density is going to be in, it's what? It's mass per volume, so it'll be grams per liter. So that's kind of what you're going to get. And the density, it'll be the density of this, like, small flask here. So here's kind of the deal with the lab, all right? You ready? I'm going to give you an unknown, and you're going to put a little bit in. Well, you're going to weigh all this stuff dry, and you're going to put a little bit then afterwards into the bottom, just a few milliliters. And you might say, well, don't I have to know how much I put in? No, here's why. You're going to take your glass foil, and you're going to put a really tiny pinhole through it. Boop. And then you're going to heat this. But I'm going to heat it in the water instead of heating it directly. So it's like calling it, in the kitchen, we call it a double boiler. So we're going to lower this thing carefully down. And you want as much as you can of this thing to be in the water without getting the lid wet. You don't want to get that wet. And I'm already hitting against the lid. So if this was me, I'd have to add some more water, almost up to the tippy top, okay? Now, then, should I do that? I should do that.
Without getting the lid of the top.
Yeah, you don't want to get the aluminum wet because otherwise then you weigh it later afterwards and then it's too much weight. They have you do this in the lab in a hot plate and it takes frickin' forever. So we don't do that. Okay, we use a Bunsen burner and you keep track of the temperature of the steam in there when it starts to become vapor by just getting the same temperature, hopefully, of the water bath. If you just stir a little bit, you should be able to get that temperature. Now, you don't know when it's going to vaporize, so the first trial is the hardest. But once it vaporizes, then it starts, you're going to see the amount of the liquid is going to go like this, right? It's going to start coming out of the little hole at the top, the little tinfoil hole. So you won't see that, but it's going to be coming out. You'll see less and less. And what's in there is called a boiling stone. The boiling stone just kind of moves around to distribute the heat. And the last little drop of liquid will cling to that stone. And that's kind of when you want to go, okay, we're there, stop. And then you want to measure a lot of things at once. You want to measure the temperature of the water bath, which hopefully is also the temperature of the gas in there, right? So think Pivnert. So I need the temperature of the gas. So that would be the same as your water bath. Then you're going to take this thing off with hot gloves that I'll have. Ay, caramba, that shouldn't happen. All right, maybe with hot gloves you can do it this way. Just take it out. And I've got the hot gloves on. Do you see them? Okay. And you're going to cool it just briefly underwater like that without getting the top wet. Just in one of the back ones. And we're already done. It only takes like a few seconds to cool it because it's a gas. Now use the back ones. This front one's terrible. Okay. Anyway, that's about it. Then you're going to dry it all off and you're going to weigh the thing afterwards. And what you'll get is the weight. And interestingly, when you cool it down, guess what some of the unknown gas will do?
It'll go back down.
It'll go back down and become a liquid again. And that's okay, because you know what the temperature was at that moment when the gas totally filled the beaker, if you know what I mean, or the flask. So bear with me. You're going to get all this in instructions anyway. But I want to run through it once because you're going to do a little practice run today. Okay, so I dry all this off. I weigh it again. So I've got the weight of the gas that filled this. I have the pressure because we're going to look it up on the barometer in the back room each day. Whatever number of atmospheres or millimeters of mercury, I'll tell you, and I'll put it on the board. So PV, no, the V, well, you're going to do 3 trials, but at the very end, you're going to have to pour out actually, no, at the very end, you can just leave the boiling stone in there. It doesn't matter. And you need the volume of this flask, but it's the volume, not the numbers on the side, because those are too little, but it's the volume until the very, very tip top. You need the whole thing, because the whole thing is what the gas filled to. And then I got to take that carefully, and to get the volume, pour all this into a what? What would be an accurate thing to measure volume? What tool, Tom?
The graduated cylinder.
Exactly. So pour it into a big graduated cylinder in parts if you need to, and carefully so you don't lose any of the water. And then you'll have the volume, you'll have the pressure, you'll have the temperature, and the R value, so you can solve for the number of moles of your stuff. And you'll also have the weight of your unknown at the end. And that's enough to give you the density. At any rate, you can figure out the molar mass of your unknown. And that's how people do it sometimes with chemicals in the lab. So it's a good old method of doing and finding the molar mass of a gaseous substance. So what you're going to do today is sort of a pre-lab experiment. Oh, sorry. Let's look at the picture, because that's good too. Check out the picture on page 3. Instead of a hot plate, you can put like Bunsen burner underneath, burner next to it. I'm giving you the procedure. You don't have to write up the procedure. You can just use this one. And you want to read it, you and your partner. And you can see eventually later there's calculations to do, and they give you a nice data sheet. How sweet is that? Identification code, no, we don't have one. So there's just the unknown. And I'm hoping on the Monday, because we prep for it now, on the Monday you'll get 3 trials in. That's my hope over the 2 periods. The first one takes the most time because you're trying to figure it out. Noah.
On the picture, it says support ring. What is that? Aren't supposed to.
I don't know why they have that there. The only support you've really got is this pad to support the beaker that you're going to have the hot or the water that you'll heat up in. And then underneath here, you're going to have your Bunsen burner. So ours will be a tad different than that. But I think the other stuff is right. You got your aluminum cap, you got your pinhole, got your thermometer. They have the thermometer in a flask. You can just hold it. You don't have to do that. I found that if I put the thermometer in a second flask like that, it ends up being like a big, hairy mess of stuff. And students can't even get the thing out to cool it very quickly at the end. So just hold the thermometer. You can cross out the flask here for the thermometer if you want. Other questions from you, roughly about what's going on here?
So what do we do after? I didn't quite get the last part. What do we do after we've measured all of it?
Before you get the volume, because now it's all wet, right? Before you get the volume of the actual flask, you'll do that after all 3 trials, to be honest. No, before that, you're going to take each time this thing, once you've cooled it, and take it in the back room and get the mass of it. And then you can subtract out the mass of everything that was before it was, when it was dry, and you get the little mass of the unknown that used to be in the gas form. And that will lead you to getting the density and then figuring out it with that formula number 9, the molar mass of the substance. I know it's kind of a lot to take in, but it's an AP lab. So by the time you'll do it, I think you'll be ready. Okay, here's the pre-lab assignment. You can work on it and talk to each other about it, okay? Make sure you're all getting the same answers. And I'll give you an extra one for Leah too. So she's all ready to go as well. I'll help you out if you get stuck on this. Yeah. We'll talk about how to write it up too today in the lab. So mainly you write everything on the lab stuff that they provide for you. And, Tom,
What do you write for the section header? What does that mean? Section. Is that like 11B?
no, just leave it blank. That's, I think, for really big schools that have 3 or 4 AP classes.
Oh,
So we're not that big.
I see it's safety.
Yeah, what aspect is safety?
I don't want to inhale some random thing you just boiled.
That is so true. I did that once, and it was not good.
What did you inhale?
Something that had a lot of ammonia.
oh
So you,
Almost made my nose bleed.
Really?
Oh God.
well, don't do that.
Thank you. I wish you were right at the time, man.
Yep.
Where were you 20 years ago?
Safety, as Mr. West.
So the answer to number 1 is just like not to inhale the gas. So you don't inhale the gas.
Of course, now you can answer number 1 with COVID too, but that's not what they mean. Okay, so folks at home, I'm going to send you this. So here's the pre-lab and the lab itself. So I'm going to go make a scan of this and send it to everybody right now. Maybe somebody in the class chat can tell Chipper she's going to get this.
I think it was when there's like a very small amount of water on the boiler.
Yeah.
There's some, I think there was something else as well.
When there's no more.
The last drop was.
I mean, you just gotta look. Or I guess it would be like, oh, I think it's the boiling stone because you wouldn't really be able to see it. It's just like residue on the base of it. But like if it's a significant enough
You
amount.
stop it when there's no more liquid left to see, and the rest of it has been absorbed by the floor.
Absorbed.
Yeah.
Oh, like it's I said when there's a small amount of liquid flake in the boiling stone and there's no other.
Yeah.
Okay.
Yeah, I mean.
For one, do we know what kind of gas it would make?
Is that called a cylinder?
Graduated, so. Well, I guess it's an unknown difference, we don't really know.
For number 1, like you said, so that you do not inadvertently know the unknown things.
Yeah,
Wait, which was essay?
I just remember one,
No.
because I thought maybe that he mentioned ammonia, and I was kind of spaced out, and I thought he was saying it was gonna be ammonia gas.
No.
Okay.
We're saying he inhaled it once.
How would you measure
Living life.
Intentionally as well.
Yeah.
Yeah,
Puffing ammonia.
you can't like
It is
How are you,
grab a bunch
like,
of things,
standing
you could
here?
grab a bunch of bottles out of the chemical shop, pour them into water, and then boil the water, and then pump it.
Living life.
So it gives you the mass already, like
Yeah. Yeah, well, it gives you the,
Wait, at
Yeah.
some
Oh, the
point,
moment they want it.
at some point, we have to measure
Yeah, they want
the,
that.
or we have to
Yeah.
weigh the weight, or we have to weigh the tinfoil cap.
Yeah, before and after, so that was good.
You have to calculate the magic on those to track.
Oh,
One
no,
of those
we'll
per-
Oh,
Yeah,
wait.
I'm sorry.
Can't solve the math.
Oh, yeah, okay.
It's going down, it's a
It's
weird
confusing
order.
way after. Why should you know what it's okay. I slept 2 hours. I didn't hear what he said.
That's just
Why only
if
2
it does.
I don't know.
We don't have a lot of work.
Yeah, I think everyone has their own. We all have the same class.
Okay, so folks at home, I'm going to end this broadcast and just say that you'll have that lab with you.